All right, this is baby real analysis problems, and this will be problem 11. And I've broken this problem up into part A and part B, where part A comes from the Bartle's textbook and part B comes from J. Cummings' textbook. Now I put these as into one problem because they both encompass the same kind of idea as far as how we do the problem, and also the fact that both of them involve sequences that are defined recursively. So part A is a problem from Bartle's Intro to Real Analysis, 4th edition, and it's exercise 3.31. And also, I didn't write verbatim what the question asks. I kind of just condensed it so that, but what I do to work out the problem does meet the requirements of what the question does ask in the textbook. So the first one's exercise 3.31 from Bartle's textbook, and it says x1 is equal to 8, and then we're defining it recursively so that the n plus 1 term is equal to 1/2 times the nth term plus 2. Of course, and then n's a natural number. So we're going to show that this sequence converges and then find its limit. And then part B is J. Cummings' Real Analysis Long Form Mathematics textbook, and this is exercise 3.24, and it says let a1 equal the square root of 2, and then the n plus 1 term equal the square root of 2 plus the nth term. So I'm going to show that this sequence converges and actually show that the sequence converges to a specific value 2. So 3.24, we're pretty much given the value that we're needing to show that it converges to. Whereas in this exercise, we have to find the value that it converges to, but still prove it. All right, so the idea that's going to be used for both of these proofs is the monotone convergence theorem. So the idea to prove these two examples or two exercises we're going to use the monotone convergence theorem. And so I'm going to abbreviate that as MCT. And it basically says that if you have a monotone sequence, so if some sequence AN is monotone, meaning it's either in monotone increasing or monotone decreasing, so if it's monotone, increasing or decreasing, then the sequence is bounded if and only if it converges. So it's bounded if and only if it converges. And we can actually go, it goes further on, we could say, so furthermore, if the sequence is monotone increasing, then the limit itself, so the limit of the sequence AN, it's equal to the supremum of the values of this in the sequence. And then if it's decreasing, then the limit is equal to the infimum All right, so that's just, and it's more specific. We can say, so if it's a monotone sequence, so it's increasing or decreasing, then the sequence is bounded if and only if it converges. And then it goes more specific than that. Once we know it's an increasing sequence, and the limit actually is the supremum. And then if it's decreasing, then the limit is the infimum. So I will say that, note, it is often difficult to show if some value is a supremum or infimum as far as for sequences. And so when I calculate the limit, I will use the concept that the nth tail of sequence AN converges if the sequence AN converges. So I'm going to use the concept that the nth tail of the sequence converges when the sequence itself converges, further they converge to the same thing. And you'll see when I get to this first exercise, when I do find its limit, I'm going to use this concept of the nth tail converging to the same value that in which the sequence converges to find its limit. That's easier to show than determining if some value is the sup or nth, at least in my opinion. And so the nth tail of a sequence is basically the sequence A subscript m plus n. Well, n is a natural number, and this is for some value m. So if I wanted the one tail, so for instance, the one tail is the sequence A, so it'd be like 1 plus n, or just n plus 1, just switching it. And so if we know some sequence AN converges to A, then we know that the one tail also converges to that same value A. All right, so that's how I'm going to use that concept when I calculate its limit. All right, so that's nth tail of a sequence, and an example of that is the one tail, where you're using the value 1 for m, and it's just the sequence or subsequence a subscript n plus 1. All right, and then as far as the monotone convergence theorem, I'm going to basically use the fact that, okay, if it's monotone, meaning it's increasing or decreasing, and then if I show it's bounded, then it converges. All right, so the first exercise, so part A, and this is from Bartle. And it was exercise 3.31, so chapter 3, section 3, exercise 1. So we have the sequence x1 is 8, and then the n plus 1 term is defined to be 1/2 times xn plus 2. And I need to show it converges and then find its limit. Okay, so to show it converges, so I'll break this up into 2 parts. So the convergence part. We're going to use the monotone convergence theorem, meaning if we show that it's monotone, so we first show our sequence is monotone, so increasing or decreasing. And then if we can show that the values of the sequence are bounded, then we can conclude that it converges. All right, so that's how this is how the proof is going to be structured. Now the other part for finding its limit, I'm going to use that concept of the nth tail. So use what was mentioned earlier about the nth tail of a sequence. All right, so that's how I'm going to do this problem. All right, so the first part, we're showing it converges. So I claim that this sequence is monotone. And let's see, so specifically it's monotone decreasing. In other words, the sequence is such that in other words, that we have so that the terms x1 is greater than or equal to x2, greater than or equal to x3, and so forth, is greater than or equal to xn, greater than or equal to xn plus 1, ... So that's what I'm going to show for decreasing. And I'm going to use an inductive proof. So this will be induction proof. So do PF for proof. So the base case we have that x1 is 8, x2, because our sequence is defined to be the first term's 8, then the next term is going to be 1/2 times the previous term, and then plus 2. So x2 is going to be 1/2 times x1 plus 2. Well, 1/2 of 8, so that's 4, plus 2 is 6. So we have that x1 is greater than x2. Now you could try x3 just to go demonstrate it further. That's 1/2 times x2, then plus 2. Well, x2 is 6, so that's 1/2 times 6 is 3. 3 plus 2 is 5. And so we have x1 is greater than x2 greater than x3. All right, so that's the, we've done the base case. Now, assume it's true. That x sub k is greater than x sub k plus 1 for some k. All right, so then if that's true, so if this is true, xk is greater than xk plus 1, then that's if and only if I can multiply both sides by a half. 1/2 xk is greater than 1/2 of xk plus 1. Well, then I can also add 2 to both sides, so that's if and only if 1/2 xk plus 2 is greater than 1/2 xk plus 1 plus 2. And based on how our sequence is defined, this part is really xk plus 1, since the k plus 1 term is equal to 1/2 times the kth term and then plus 2. So this would be if and only if x sub k plus 1 is greater than, and then since this is k plus 2 or k plus 1 for the subscript, this whole thing is x subscript k plus 2. And so we've shown inductively using our assumption that x sub k is greater than x sub k plus 1. We've shown using that assumption that we got that x sub k plus 1 is greater than x sub k plus 2. So this was like the k plus 1 case. So we've shown by induction and then again this is for a fixed k. So then for all n, indices n, we've shown that xn is greater than or equal to the x subscript n plus 1 for all n. So that's meaning we have it being decreasing sequence. All right, so that's how we've shown that first part, the claim of it being decreasing. Now, the second claim is that we need the sequence to be bounded. All right, first note that since how the sequence is defined, since the first term is positive, Since x1's basically greater than or equal to 0, then we have that the n plus 1 term is going to be 1/2 times the nth term plus 2, multiplying 1/2 by a positive number, and then adding another positive number makes it still positive. So we could at least say that this is greater than or equal to 0. So we know 0 is a lower bound. Because of how the sequence is recursively defined. All right, and so I need to find an upper bound. And 0 is just a lower bound. There could be other lower bounds. All right, that doesn't have to be the, I guess, the nth in this case. As long as I have a lower bound. So 0 is a lower bound because I know at least the first term, x1 is 8, which is a positive number. And then I'm keeping recursively defined by taking 1/2 of the previous term. Well, the previous term is positive, so you're doing 1/2 times a positive number is positive, and then adding on a positive number because it's adding on 2, which makes the whole quantity 1/2 times x sub k, and then plus, or x sub n, and then plus 2. That quantity itself is always going to be positive. And we could be more careful by saying the inequality is being greater than or equal to 0. So I could be careful about that and use that 0 is a lower bound. Now for an upper bound, we know the sequence is decreasing. So to find an upper bound, consider 8. Well, 8 is equal to x1. All right, so we have that at least x1 is less than or equal to 8. And we know for all n, x sub n is greater than or equal to x sub n plus 1. And so we have 8 equal to x1, which was greater than x2, greater than ... and then xn, which is greater than x sub n plus 1. And so we have 8 is going to be greater than all of the values greater than or equal to all of the terms in the sequence, because the sequence is decreasing. So since xn is decreasing, and the first term at x1 is equal to 8, then we have that all the values in the sequence xn are less than or equal to 8. So that means 8 is an upper bound. So then we have, so for all indices n, we have that the sequence is bounded between 0 and 8. So our sequence is bounded. All right, so we've shown by the 2 claims that it's bounded. We showed that it's decreasing inductively. We actually know since it is decreasing, we would show, I use that fact for the upper bound part of 8 being an upper bound, since the first term is 8, and all the other terms are going to be less than that value 8. And then 0 was the lower bound because all of the terms are going to be positive by how the sequence was defined. All right, so by monotone convergence theorem, xn converges. So now I just got to find its limit. All right, so to find its limit, I'm going to use the nth tail concept. So to find its limit, I'm going to let the limit just be some value. Let's say let x equal the limit of the sequence. So by the nth tail, I guess it was a theorem by what was mentioned earlier about the nth tail. I'm going to use the one tail. The one tail, where it's x subscript n plus 1, also converges to x. Okay, so we have that limit of xn plus 1, or sorry, limit of xn equals x, and that itself equals the limit of x subscript n plus 1. Well, what was the n plus 1 term defined to be? So the n plus 1 term was defined to be 1/2 times the nth term plus 2. So we can say that x is equal to the limit 1/2 x sub n plus 2. Well, the limit of xn is x, so we could say x is equal to 1/2 times x plus 2 because of the limit of xn we were saying is just equal to x. So now I can find x. So I just subtract 1/2 x from both sides. That'll give me 1/2 x is equal to 2. Then I can multiply both sides by 2. And that'll give me x is equal to 4. So that's our limit. And that pretty much completes the problem. All right, so hopefully that makes sense. I used the one tail of the sequence. That's a subsequence. There is something where we talked about was subsequences converge to the same limit of a sequence if the sequence converges. But I just used specifically that the nth tail is going to converge to the same limit, and then I used the one tail where that's x subscript n plus 1. And I define, well, n plus x subscript n plus 1 is 1/2 times xn plus 2. And that itself is equal to the limit of xn, which is x. And so I just sub in x in for the limit of xn, and then I solve for x, and that gave you the limit being 4. All right, so that's where I'll stop this video. The next video, I'm just going to jump straight into J. Cummings' example or exercise. That was the part B. So I did part A. I'm going to jump into part B, but I'm not going to go too detailed like I did in this video over the concepts I'm going to apply. pretty much it's going to be the same thing. I'm going to show it's bounded, show that it's monotone, conclude that it converges because it's bounded and monotone, and then I'm going to actually calculate its limit and show that it's equal to 2. All right, so that's going to be the next video.